Assalamualaikum. A very good morning. Okay, so we are going to continue with our lecture 9. So now it's a part 3 of lecture 9. So from the previous part 2 of lecture 9, we have learned about the principles of operations, yeah, of photodiode. So that is the last part, yeah, last section of part 2 lectures. Yeah, we have learned about the operations, the fundamental, the working procedures of the photodiode. Yeah, so I hope you understand that from this part 2 of lecture 9, we have learned that the light incidence and the photo incidence will be at the depletion region. So this is where the carrier pairs are said to be generated, yeah, at this depletion region. Okay, so the carrier pairs that were generated will be then flowing, yeah, within the PN junction, and it will then produce the current externally to the circuit. Yeah, so this is what we have learned in uh, last part of last part of lecture 9. Yeah, second part lecture 9. Sorry, second part lecture 9. Right. So for today's lecture, we're going to start our learning today with the topics of type of semiconductor of photodiode, yeah, type of semiconductor photodiode. So basically, there should be two categories of a semiconductor photodiode that we need to know. The first one is the photodiode without the internal gain. So this include the PN junction, yeah, the PN junction, and also another one is PIN junction, yeah. So we have PN junction and also PIN junction, in which this type of semiconductor photodiode, which is without the internal gain, is said to generate a single electron hole pair per absorbed photon. Okay, so that's what we meant by the photodiode without the internal gain. The second type of photodiode is a photodiode with the internal gain, and this is including the avalanche photodiode, the APD, yeah, avalanche photodiode, and also phototransistors. So our interest will be on the first one, which is on the avalanche photodiode, which will be discussed later in this lecture. Yeah. So what is the effect of photodiode with and without the internal gain? Okay. So for photodiode without the internal gain, so we know that for this kind of photodiode, it will generate a single carrier pair based on one absorbed photon. Okay, so this is the photodiode without the internal gain. Yeah, but for the photodiode with internal gain, we are going to have a case whereby a high reverse voltage applied, yeah, which is a reverse voltage, yeah, reverse bias voltage applied. So this will accelerate the carrier pairs, yeah, accelerate the carrier pairs, which is the electron hole, but which were produced by the photogeneration, yeah, process. So these carrier pairs will collide with other carrier atoms. So you can see the things here, right? So the carrier pairs which were generated by the photogeneration. So these carrier pairs which is moving or which was said to be accelerated by the highly reverse voltage will collide with other carrier atoms, and this collision will further produce a new pairs of carriers. Okay, yeah. So I hope now you can differentiate the difference between the photodiode without internal gain and with internal gain. So for photodiode without internal gain, the case is that the carrier pairs is solely generated by the photon absorption, whereas for the photodiode with internal gain, for instance, the APD, apart from the carrier pairs produced by this photon absorption, will also produce another carrier pairs due to the collision, yeah, of the photo-generated carrier pairs, yeah, collision of these photo-generated carrier pairs with other carrier atoms. Yeah, so there are two mechanisms of carrier pair generation in photodiode with internal gain. The first one is the primary photon absorption. Okay, so when we have photon absorption, the carrier pairs will be produced, be generated. And the second mechanism is the collision. Yeah, collision of the carrier pairs with another atoms, which will then produce a new pairs of electron hole. Okay, so I hope by now you understand the difference between photodiode categories of without internal gain and with internal gain. Yeah. Okay, so let's have a look for the first photodiode, which is without internal gain, which is the PN photodiode. This is very basic photodiode. So we have the diagram here, the figure which shows your photodiode structure. Yeah, so we have the PN junction over there. HF is the externally applied photon or light. Yeah, and it's reverse bias. Yeah, the negative terminal is connected to the P material. The positive terminal is connected to the N material. Okay, so we have the depletion region, yeah, between the P and N. Okay, and we have the diffusion region, which is for the rest of the N material. Yeah, so this is your depletion region over here. Okay, here's your depletion region. Okay, yeah, and this is your diffusion region. Okay, and the absorption region is a combination of the depletion region and also part of the diffusion region. So for this particular PN photodiode, the absorption region will not be only on the depletion side, but also consists part of the diffusion region. Okay, so that is for the case of PN photodiode. So as what we have learned previously in the part 2 of lecture 9, so we know that depletion region is produced as a result of the movement of the majority carriers for each P and N material. So for the P, the majority carriers is the hole, and for the N material, the majority carriers is the electron. So due to the reverse bias, this hole and electron will move to the terminal, yeah, will move to the terminal as a result of reverse bias. And as such, due to this movement, we are going to have a formation of a depletion region in which you're going to have a positively charged donor atoms in the N-type. Okay, so if I can redraw this for you, okay, so that is your P material, that's your N material. So we have a reverse bias, yeah, terminal, okay. All right, so we're going to have a, for this particular P, the holes will move to the terminal as a result of a reverse bias condition, whereas for the N material, the electron will move, okay, electron will move to the terminal as a result of the reverse bias condition, right? So at this depletion region, okay, we're going to have for the N material, at the depletion region, we're going to have a positive charge, yeah, a positive charge, which is basically a positive charge of donor atoms. Okay, so that should be the positive charge. Whereas for the P material, you're going to have a negative, yeah, you're going to have a negative charge of acceptor atoms. Okay, so that should be your depletion region. Yeah, that should be the depletion region, which is a negative charge at the P material and positive charge in the N material. So this is what we have learned previously in part 2. So I just repeat it, yeah, in case you forget about this depletion region formation. Yeah. Okay. So this is a result of majority carriers which are swept to their majority side. So we have discussed this before. Yeah. Right. So basically, the width of this particular depletion region will be depending on the doping concentration. Yeah, doping concentration is understood to be looked like that. Okay, and the photons, yeah, so as because if we base on this diagram, absorption region happens in the depletion region and also in the diffusion region for the case of the PN photodiode. So it can be said that the photon will be absorbed in both depletion and the diffusion region. Okay, and as such, we can say that your carrier pairs, the electron and holes, will be also produced or will be also generated in this depletion region and also diffusion region. Okay, so in the depletion region, as what we have learned from the previous case, yeah, the carrier pairs are said to be separated, yeah, or drifted, yeah, can we say drifted under the influence of the electric field, yeah, influence of this reverse bias field, yeah. So when we have a reverse bias, we have a electric field, negative and positive, and as such, these particular carrier pairs will be drifted under the influence of these reverse bias voltage, okay. But in the diffusion region, uh, there is no drifting, but it will be a process of diffusion, the process of diffusion of the holes towards the depletion region, okay, towards the depletion region, in which it can be said that for the second mechanism of diffusion in your in the N region or in the diffusion region here, in this particular region over here, the movement, the process is very slow as compared to the previous drift process in the depletion region. Okay, so you hopefully by now you understand that in the PN photodiode, there should be two mechanisms of movement of the carrier pairs. We have a drifting of the carrier pairs, which happens in the depletion region, and we also have a process of diffusion of the holes, which happens in this diffusion region. Yeah, and one more thing to be bear in mind is that the diffusion process will be slow as compared to the drift process, yeah, of the carrier pairs. Okay. All right. So from the previous slide, yeah, we can see that due to this slow diffusion process, yeah, slow diffusion process as compared to the drift process, it's going to have a limitation of the response of the photodiode, yeah, because due to this slow movement of these carriers, you're going to have a very slow response of the photodiode, yeah, so that should be a drawbacks of the PN photodiode, yeah, which a slow response, yeah, and we prefer the photons to be absorbed only in depletion region, because we know that at this particular depletion region, the drift process will be produced or will be carried out. Yeah, the drift process of these majority carriers will be carried out in the depletion region. So as such, you're going to have a faster movement of your carrier pairs. Yeah, and as such, the response of the photon will be better. So that is why we want to have a depletion region to be made as long as possible. Yeah, to be made as long as possible, in which by this we can reduce the length or the width of the diffusion region. So this can be made, this can be can happen. Yeah, we can make the diffusion region to be as long as possible by decreasing, yeah, decreasing the doping of the N type material. Okay, so that should be the alternative that can be made, in which we can reduce, or we need to reduce the diffusion region by increasing the length of the depletion region for the case of the PN photodiode. Okay, so this is the typical output characteristic based on this diagram. It's the typical output characteristic for the reverse bias PN photodiode. So if we can refer to this graph of the IV characteristics, we have a dark current where there is no input light. So I've mentioned this in part 2 of lecture 9, in which we have the minority carriers, yeah, minority carriers in your PN material, okay, and the movement of these minority carriers without the excitation of photon will also produce the current in your external circuit. So this current, which is produced by the flowing of minority carriers, is called as a dark current. And this happens without any photon excitation to this semiconductor photodiode. Yeah. All right. We can see that when we have high light level, yeah, so we have high light level and we have low light level. We can see that when we have high photon absorption, yeah, high light level means we have higher photon absorption. We can see that the current value, the output current, the photon current produced is higher as compared to the low light level, which means that we have higher number of photons excited, yeah, excited to this particular photodiode, and as such, when we have higher photon excited on your photodiode, the carrier pairs will be increased, and as such, more current will be produced. Okay, so hopefully by now you understand about this concept of photodiode, especially the PN photodiode principle of operations. Yeah. Okay. So we have the second types of a photodiode without the internal gain, which is the PIN photodiode, and this is your figures which shows the PIN photodiode. Okay, so this is quite different than what we have learned previously for the case of PN. Okay, HF is your outside or the photon excited on this PIN photodiode. Yeah, so it's reverse bias. So we have the P material, we have the N material, and I here basically is the N type material, which is lightly doped. Yeah, lightly doped and can be considered to be intrinsic. So this is basically the ideas of reducing the length of diffusion region and increasing the length of depletion region. Okay, so the PIN photodiode basically is the improvement of the PN photodiode before. Yeah, so by lightly dope this particular N type material, yeah, we can then reduce the diffusion region and we can have a longer depletion region. Yeah, so if you base on these figures, so the depletion region here is quite wide. Yeah, it's very wide, and this is where the photon absorption is said to happen. Yeah, so it can be said that PN photodiode is the improved versions of the PN photodiode. Yeah. All right. Okay. So I think you have now understand a comparison between the PN photodiode and the PIN photodiode, in which the PN photodiode do have depletion region and diffusion region. So when we have this region of diffusion, the response is slower. Yeah. But for the case of PIN photodiode, there is no diffusion region, only a depletion region uh, exists. Yeah. So when we have only depletion region and the absorption of the photon happens at this depletion region, so as such, more carriers pairs will be produced at this depletion region and more current will be produced, and also the response of the photodiode will be better. Okay, so that is for the case of the PIN photodiode. So this is the example of the PIN photodiode, okay, which include the front illuminated, yeah, front illuminated PIN photodiode, and also side illuminated. So for the front illuminated, the photon is excited on the top of your photodiode structure, whereas for the side illuminated PIN photodiode, the photon is excited, or the light is excited at the side, yeah, the side of this photodiode, yeah. Okay, this is for the case of indium gallium arsenide PIN photodiode. So we have few layers here of these PIN photodiode which involve this indium gallium arsenide material. Okay, so this is just a sample, yeah, a structure example of the PIN photodiode for the case of front illuminated and side illuminated. Okay. Okay, so this is the third type of photodiode, avalanche photodiode, which is under the category of photodiode with internal gain. So we have learned before that for this case of photodiode, the mechanism of the carrier pass generation were actually produced by two mechanisms. Yeah, the first one is the normal photogeneration process, and the second one is the collision with between the generated carrier pairs and the new atom which produce a new carrier pairs. Okay, so that is the characteristics of avalanche photodiode, the APD. Yeah, so this is the structure of your APD. Yeah, the structure of the APD. Again, it is a reverse bias of your photodiode, yeah, or the PN junction. So it is quite a complicated or sophisticated structure than the previously learned PIN photodiode, yeah, PIN photodiode, in which for this particular structure of avalanche photodiode, it can create a very high electric field region. So I mentioned here is about 3 times 10 power of 5 volt per centimeter. Okay, so the reason for having this high electric field region is that it can speed up or it can accelerate the newly formed, the newly produced carrier pairs. So when these carrier pairs were actually accelerated, so it can then have a sufficient energy to collide with a new atom, and it will excite a new electron and hole pairs. And this process is also known as impact ionization process, which is avalanche process of creating new carriers. So Things to be remembered for the case of APD is a formation of high field region, yeah, a high field region, where in this particular high field region, we're going to have a collision of the carrier pairs, yeah, with the new with the atoms, and which will create new electron hole pairs by a process known as impact ionization process. Okay, and this process of impact ionization can create more free carriers, and it is based on a factor known as multiplication, or also a gain factor of m. Okay, so we have a multiplication or gain factor of m, which is a factor that determine the generation, yeah, of the new free carriers as a result of impact ionization process. Okay, so we can see that for this particular case, we have a high gain region where we can see that there is a high electric field region at this particular N and P region. Okay, and there is a absorption region where the photon is said to be absorbed, yeah, at this particular position. Okay, this is a normal process of photon generation, and a process of impact ionization is produced at this high gain region here. Yeah. So this is a characteristics of avalanche photodiode, and hopefully by now you understand the difference between the PN, the PIN photodiode, and the newly covered avalanche photodiode here, which is under category of photodiode with internal gain. Yeah. Okay. So for the multiplication factor of the APD, which is due to this impact ionization process, so we can actually calculate the value of the multiplication factor M, yeah, and in which the M is measured by this equation, yeah, M equals to I over IP, in which I here is equals to the total output current at the operating voltage, which is a output current produced after this multiplication process, whereas IP here is the initial current or the primary photocurrent before the carrier multiplication process occurs. So I here can be also returned to be the current produced after the impact ionization process, whereas the IP is the current before the impact ionization process takes place. Yeah, so that should be the values, the ratio of the values of current, which can be used to calculate the multiplication factors or the gain factors. Yeah. Okay. So this is a comparison between the PIN photodiode and the APD photodiode for three types of semiconductor material: the silicon, the germanium, and indium gallium arsenide. So basically, the operating lambda should be similar. The gain is very much different as compared to if we see this table here. We know that for the APD, due to the M, due to the multiplication factor, the gain will be very high as APD as compared to the PIN. Okay, for the dark current, yeah, for the dark current, the value is nothing much different for the germanium, but for the silicon, we have a difference there, 1 to 10 for the PIN, whereas for the APD is 0.1 to 1, which is a reducing value. Yeah, whereas for the indium gallium arsenide, we have a reduction value of the dark current. Yeah. For responsivity, we can say that a responsivity for the APD will be high as compared to the PIN, because we know that for the equation of responsivity, the R is equals to the output photocurrent, the I, the produced photocurrent value divided by the incident optical power. So we know that for the case of APD, the RP will be very high because of the effect of the avalanche process or the impact ionization process. So as such, the value for responsivity for the APD will be very high as compared to the PIN photodiode. So the response time, yeah, the response time is somehow similar. It's about similar for both cases of PIN and APD. And for the bandwidth, we can see that the value is same for the indium gallium arsenide for both PIN and APD. For the silicon, so we have a slight changes, while the germanium we have quite a different changes between the PIN and the APD photodiode. Yeah. Okay, so this is a comparison between the PIN and the PD. So our concern must be concentrated on responsivity. Yeah, responsivity will be very much different for the case of APD as compared to the PIN due to this formulation. Yeah, right. And you can see that the gain is very much different for the case of APD with respect to the PIN. Yeah. Okay, so hopefully by now you have understand about the type of photodiode without internal gain and with internal gain and the comparison between those photodiode structures. Yeah, right. So let's have a look at this example of photodiode. Okay, so we are given for the first example here, we are given a 10 to the power of 11 photons per second with an energy of 1.28 times 10 power of negative 19 joule incident on the ideal photodiode. Yeah, so it's ideal photodiode. Yeah, so when you have ideal photodiode, it means that your eta is equals to 100%. Yeah, so you have to remember that. Okay, so the question is calculate number one, the wavelength of the incident radiation. Number two is the output photocurrent. And number three is the output photocurrent if the device is an APD with a multiplication factor of 18. Okay, so this is the case whereby we have a photon incidence of 10 to the power of 11. Energy of the photons is 1.28 times 10 of a negative 19 joule. Okay, and the photodiode is ideal in which the quantum efficiency is 100%. So number one, need to calculate what is the value of the wavelength of the incident radiation. Okay, so for this calculation of wavelength, we need to go back to these long wavelength cutoff values just now. Sorry, in the second part of lecture 9. So we have learned that for the wavelength value can be calculated by using this equation. Okay, lambda C equals to Eg divided by the Hc. So this is the maximum wavelength that can be supported by this photodiode. So we have that the energy, the Eg is equals to 1.28 times 10 power of negative 19 joule. Okay, so that should be the energy of your photodiode. Yeah, so 1.28 times 10 negative 19 joule. Okay, your Planck constant is 6.62 times 10 of negative 34 joule seconds, whereas for the C will be 3 times 10 power of 8 meter per second. So for this lambda C, I mean for this cut-off wavelength, it can be further calculated that the wavelength of the incident radiation will be equal to 0.64 micrometer. Okay, so that should be the wavelength of operation, which is the maximum wavelength that is applicable, that is permissible, having with this given energy of 1.28 times 10 power of negative 19 joule excited or incident on this photodiode. Yeah, so that should be the answer for part A of the questions. Okay, so let us proceed with part B of the questions. So part B of the questions is to calculate the output photocurrent. Yeah, so let me erase this answer first. Okay, so for this case, the part B of the questions is to calculate the output photocurrent. Okay, so for this calculation, we know that the responsivity, yeah, responsivity is one of the equation that can be used to calculate the output photocurrent, because we know that from the equation that we have learned previously that responsivity is equals to the output photocurrent divided by the input optical power. Okay, so this is the equation for the responsivity, which will be used to calculate the value of input photocurrent. So we know that this responsivity can also be calculated by the equation of eta, which is your quantum efficiency, multiply with the charge amount, multiply with the lambda, divided by the Planck constant, and multiply with the speed of light. And this will be equals to the photocurrent value divided by the input optical power. So from here, from this calculation, we know that the eta is 100%. The E is known to be 1.6 times 10 of negative 19. Lambda is from what we have done previously. H is known and C is known. We can then calculate this ratio of photocurrent divided by the input optical power. Okay, so from this particular equation, okay, we can say that this in photocurrent, sorry, the IP over the P in, yeah, will be then calculated to be 100%. So we just use 1 as the quantum efficiency. E will be 1.6 times 10 of negative 19 joule, yeah. Lambda is 0.64 times 10 of negative 6 meter divided by H, which is 6.62 times 10 of negative 34, 34 or joule second, sorry, joule seconds, yeah. Whereas for the C is 3 times 10 power of 8 meter per second. Okay, so from this calculation, we can see that the ratio between the IP over the P in is calculated. Yeah, we calculated this value. So the value for this ratio will be equals to 0.515. So that should be the ratio of the photocurrent, output photocurrent with the input optical power. But our interest will be on the output photocurrent. So we need to find out how to calculate this input optical power. Okay, so the values of photons, which is 10 power of 11 numbers of photons, can be used to calculate the input optical power, yeah, because input optical power is can say proportional to the number of photons excited, yeah. So from the formulations of the input optical power, sorry, the rate of photons, sorry, yeah, the rate of photons, I can see the rate of photons is equals to the input optical power divided by the HF. Yeah, input optical power divided by the DHF. So this is a formulation used to calculate the input optical power, where RP here is your photon rate. Yeah, photon rate. So in this case, the photon rate is 10 power of 11 photon per second. So from here, we can have 10 power of 11 shall be equals to the P in multiplied by H, yeah, which is 6.62 times 10 of negative 34, okay, multiply by the C, which is 3 times 10 power of 8 meter per second. So from this calculation, we can see that the value of the input optical power shall be equals to 0.031 microwatt. So that should be the value of input optical power. So when we're substituting this input optical power calculated using this equation, we can then use it to find the input optical power, in which when we substitute the P in into this equation, you're going to get your input optical power IP shall be equals to 0.515 multiplied with 0.031 micro. So the value for the photocurrent output will be equals to 0.016. Yeah, 0.016 microwatt. So that should be the value of the input photocurrent, yeah, for your case. Sorry, the output photocurrent produced by this photodiode. Okay then. All right, good. So that should be the value for output photocurrent. So we answered question B already. So let us proceed with question C, which is to calculate the output photocurrent if the device now is an APD with multiplication factor of 18. Yeah. Okay, so let me erase this answer for part B just now. So I hope by now you understand, yeah, about this concept of how to calculate the wavelength, how to calculate the output photocurrent, and so on. Yeah. Okay, let me rub this one first. Okay, let me erase this answer first. Okay, so let us proceed with part C of the question. So part C, if now the output photocurrent, the device is now an APD with multiplication factor of 18. Okay, so for the previous case, this is the answer for part B is the case whereby we assume that this photodiode is a case of photodiode without internal gain. Yeah, without internal gain. So it is either PN photodiode or PIN photodiode. Yeah. So if now your diode is an APD with multiplication factor of 18, so we can say that this multiplication factor M shall be equals to the current, yeah, current which is output photocurrent when I can say when we see that the impact process applied or happens, yeah, we can say this is equals to the IM, okay, divided by this current produced by a normal photo generation process. Okay, so this IM is a current produced by the impact ionization process or the avalanche process, whereas the IP is the current produced by a normal photo generation process. Okay, so if I can go back to the previous slide, this slide, basically it is same to this equation here. Okay, M equals to IM divided by IP. IM is the current produced by the avalanche process or the impact ionization process, whereas the IP is produced by a normal or primary photo generation process. Yeah. Okay, so it's similar to these equations that I use here. Okay, so we need to find out what should be the IM, which is the output photocurrent when the device is said to be the APD, whereas the IP here is the output photocurrent when there is no multiplication occurs, or I can say this is a normal photocurrent value. Okay, so we can see that M is given to be 18, so 18 shall be equals to IM divided by the IP, which is produced from the previous part B of the questions, which is 0.016 microwatt, okay, which is a normal photocurrent produced or generated. So from here we can say that the total output photocurrent produced when the device is assumed to be an APD with multiplication factor of 18 shall be equals to 18 multiplied with 0.016 microwatt, and the answer for that will be equals to 0.2. Sorry, this is not microwatt. I apologize. Sorry for that. This is microampere. Yeah, it's microampere, yeah, not microwatt, microampere for the output photocurrent. Okay, so basically it should be in ampere. I apologize, yeah, it's my mistakes here. So the answer for this multiplication again, for the case of the photocurrent when there is the multiplication process occurred, should be equal to 0.288 microampere. So that should be your photocurrent produced when the device is said to be an APD with a multiplication factor of 18. Yeah. Okay. So hope you understand about this example. So part C of the question, next question is about the silicon photodiode. We are given that for the silicon avalanche photodiode is APD, yeah, APD, silicon APD. It has a quantum efficiency of 65%. Okay, the eta is 65%. Okay, and the lambda is 900 nanometer. Okay, lambda is equals to 900 nanometer. So we are given now that the input optical power is 0.5 microwatt. Okay, so the P in is equal to 0.5 microwatt from the questions. Okay, and it produces a multiplied photocurrent of 10 microampere. So basically a multiplied photocurrent means that for the case of APD, this is the current produced after the multiplication process occurred. So after the avalanche process occurred. So we can see that now this 10 ampere is noted to be IM, yeah, which is a current, a photocurrent produced after the process of multiplication. Okay, so the question is, what is the value of multiplication factor of M? Okay, so to answer this question, we need to first find the value of normal photocurrent without any multiplication factor occurred in the photodiode. Yeah, so this can be calculated by using the equations of responsivity again. Yeah, where we have the equations of R equals to IP over the P in. Okay, so IP is the normal photocurrent without any process of multiplication or without any process of avalanche, yeah, normal without internal gain. So R is calculated using the equations of Eta multiplied with E multiplied with a lambda over HC, and this will be equals to IP to be obtained divided by P in, which is given to be equal to 0.5 microwatt. So from this value, we're going to have that IP shall be equals to P in, which is 0.5 microwatt, multiply with the N, which is 0.65, so not N, eta, 0.65, the quantum efficiency, multiply with this charge E, which is 1.6 times 10 of negative 19, the lambda, which is 900 micrometer or 0.9 micrometer, divided by this H, which is 6.62 times 10 of negative 34 joule second, okay, joule second unit, and then we have, this is 34, yeah, and the C is 3 times 10 8 meter per second. So by calculating this, and up you're going to have the IP, yeah, or the photocurrent without any multiplication process will be then equals to 0.235 microampere. So this is the value of photocurrent, yeah, right. Then we can use this to calculate the multiplication factor M, in which, from what we have learned previously, the M shall be equals to the current photocurrent after the multiplication process. Sorry, IM, yeah, this is IM, photocurrent after the multiplication process, divided by the IP, which is a photocurrent before the multiplication process. So we know that the IM is already given to be 10 microampere, whereas for the IP, which has been calculated just now, which is 0.235 microampere, and the answer for this ratio will be then equals to 43. So based on this, we know that the M, the factors of multiplication for the silicon APD in this particular case, will be equals to 43. Okay, so I hope by now you understand about this method of calculation of the multiplication factor for the APD photodiode. Yeah. Okay, so that's the end of chapter 5 on the optical detector, particularly on the photodiode. So we are going to learn more on this photodiode, especially on the noise calculation of the photodiode in chapter 6 under the topics on the chapter title of noise in the receiver. Okay, so this will be covered in the lectures next week. Yeah. Okay, so with that, I thank you for your attention. Okay, in case if you have any questions related to chapter 5 on this optical detector or photodiode, you can always PM me for further discussion. Yeah. Okay, guys and girls, thank you very much. Hope to see you again in the next lecture of chapter 6. Yeah. Okay, thank you and bye bye.